Welcome back. So we spent a little bit of time thinking about how to deal with charges and currents and the forces on those charges and currents due to the effects of magnetic fields. Today we're going to talk about generating those magnetic fields. And so you would say to yourself, well, if I'm talking about magnetism as a way of describing forces dealing with moving charges, then it would make sense that to generate magnetic fields, I would also need moving charges. So if I asked you to write down a mathematical model that described how magnetic fields were generated, and you knew, as you do, that magnetism deals with moving charges, you could probably write down some guesses as to what that mathematical model might look like. So if I have some charge, and I have some reference point P, you would say, well, magnetism deals with moving things, and therefore that charge is probably going to have some velocity. So the velocity vector is going to be important. You also know from your studies of electricity that when I talk about generating fields, I often have that vector r that points from my charge distribution to the point at which I'm trying to calculate the magnetic field. And of course, here that vector is also going to be important. So that r vector that points from the moving charge to the point that I'm interested in studying is obviously going to be part of this. But since it's magnetism, well, it probably is also going to include a cross product. So in putting all of these things together, you can probably guess that the magnetic field B is going to be proportional to the cross product of the only two vectors in the problem, the velocity and r. And maybe it would take a couple of tries to figure out what that cross product might look like. But it's probably going to be the cross product of it's got to be either V cross R or R cross B, but it turns out to be V cross R, divided by R squared. Now, of course, I'm going back to that definition of R hat, which is the R vector divided by its magnitude, and then probably proportional to the size of the charge that's actually moving. And this simple mathematical construction turns out to be exactly right, where I just have to allow for there to be a constant of proportionality, which we call mu naught over 4 pi, to compensate for the fact that the right-hand side of this expression is all in SI units, and I've already used up any definition of units per B when I was talking about how to parameterize the forces on moving charges. And so quickly I've been able to come up with a mathematical model that turns out to be empirically consistent with measurements of magnetic fields due to moving charges. And so I see that the magnetic field is proportional to the charge that's moving and the cross product of the velocity with the r vector. Now, as an example, you might want to pause and think about, well, if I had normal SI units and normal charges, say an electron traveling at a pretty fast speed, a couple of meters away from you, and I do out this expression, I find out that the magnetic field isn't very big. In fact, it's many, 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 many orders of magnitude smaller than even the background magnetic field that we have on the surface of the Earth. So to make big magnetic fields, I have to do one of two things. I either have to I could make R really, really small, get up and close and personal with the electrons. That's hard for me to do, but I could increase the velocity, right? I could make V bigger, but again, there's a speed limit to that, right? Nothing can travel faster than the speed of light, and so there's a limit to how quickly these charges can move. And so the only thing I really have left to do is to increase the number of charges that are moving. And of course, this is easy to do. All I have to do is hook up a circuit, right? So once I have a circuit, then I can move lots of charges through a wire. And if I move lots of charges through a wire, then I have lots of charge moving. From a calculus perspective, what that means is I'm changing Q times V, which is measurement of a charge moving at a location with a particular rate, to how much charge is there at this location moving by me, right? So the current is a measure of how much charge per unit time is moving by a particular location. And so I replace QV with I times ds. So I'm asking myself how much current, how much charge per unit time is moving through this little segment of the wire ds. And of course, ds now is this little, because it's this little segment of the wire, ds holds two pieces of information. First, the magnitude of ds is a little infinitesimal length of the wire, right? So I break my wire up. I'm usually doing, say, a Riemann sum over it, right? I break my little wire up into little segments ds. And the direction of ds is in the direction of the current I, right? So ds holds a magnitude that's equal to the length of that little section, and the direction of that little, and the direction of ds corresponds to the direction of the current. And once I have that ds, then I can relate that to, say, my point of interest, right? I have my r vector that points from that little ds to the point that I'm interested in. Now, purely from a calculus perspective, you might end up doing these integrals actually by thinking about first defining the path s, which is of course going to be some vector that describes the function, say x, y, and t, right? X, y, and z. And then if I want to find out how that thing is moving, if I want to find out how, what is the little infinitesimal ds, I often can find ds by taking the implicit derivative of the three functions that define my parameterization. Okay, so if I know what x is as, say, a function of time, or x is as a function of theta, or x is a function of whatever parameters I'm using to define my charge distribution, my current distribution in this case, then I can find ds by taking the implicit derivative of the right-hand side. Okay, why don't we do an example? So I have a little wire that's moving, in this case, in the z direction, and I'm going to let the current go upward, right? So if I parameterize my wire, I might parameterize it with respect to some variable that's natural in this problem, say z, where z is going to go from minus infinity to infinity, right? So z is going to go from the bottom of the wire to the top. Now that is the parameter of my problem, and so my path s is going to be, well, x is always 0, y is always 0, and z is going to be given by z. That's the parameterization of my path. And so ds then is going to be the implicit derivative of this, which is going to be, well, the derivative of 0, 0, 0, so 0, 0. The implicit derivative is z. Well, the only thing that z depends on is z, and so I get dz, which is of course just equal to dz in the z hat direction. Okay, so now I've defined my ds by first defining my path and then taking the implicit derivative of it. If I have some, so that defines my ds. The last thing that I have to define is r. Now, if I have some point over here, which is going to be my point of interest located at x, y, z, now I have to be careful because I've already used up z in defining my current distribution, right? I wanted to know what my path looked like. This x, y, and z represent the point that I'm interested in studying, so it's a little irresponsible of me to call them just x, y, and z, right? Because that makes it seem like it's the same thing as the variables I use for my parameterization. So why don't I call these x prime, y prime, and z prime, right? So now it's easy for me to differentiate, little joke there, between the variables that I'm using to define my charge distribution and the variables that I'm using to define my point of interest. So if I have a little bit of my parameterization, ds, and I'm pointing to my point of interest x, y, z, I can write down that the vector r is going to be where I'm looking minus where I started, which is x prime, y prime, z prime minus z. And so then now I've constructed my vector r, and I've constructed my vector ds, and so now I'm ready to plug everything into the Biot-Savart law. Okay, so here's the mathematics behind it. So I have my magnetic field is proportional to this integral of I ds cross r over r cubed. I can plug in what I know ds to be, and I can plug in by component what I know the r vector to be. And I've chosen to do it by components here because for this particular example, where I only have one component of the ds vector, it's nice for me to do this out using method number 2 of evaluating cross products, where I just deal with one component at a time. Now, in looking at this expression, I see that x and y, or x prime and y prime, play a very, very small role in this integral. In fact, They aren't variables of integration. I'm integrating over z. And they always sort of, and they kind of only appear in a couple of different locations. Well, it turns out that I can also look at the symmetry of this problem, and instead of dealing with x and y separately, I can put them into polar coordinates. So in this case, my polar coordinates are going to be rho and phi, where rho is the distance from the z-axis to the point of interest. So rho is x prime squared plus y prime squared. And phi is the angle from the positive x-axis. So using that definition, x prime squared plus y prime squared is just rho squared. And x and y can be given by the simple expressions rho cosine phi and rho sine phi. I can plug those in, and then they pull out of all of the integrals that I have to do. And so all that's left is one integral, which is the integral from minus infinity to infinity of dz over rho squared plus z minus z prime squared to the 3/2. That appears in both the first term and the second term of my cross product. There is no third term because z hat cross z hat is 0. And I only have to do that integral once. And it turns out that that integral is actually equal to 2 over rho squared. It's a pretty easy integral to do, so I'll leave it to you to do in your own time. But once I do that integral, all that's left is for me to evaluate the two cross products that are left, which is z cross x hat, which is minus y hat, and z cross x hat, which is y hat, and z cross x hat, z cross y hat, which is minus x hat. And so let me do that again. The first term has a z hat cross x hat, which is y hat. And the second term has a z hat cross y hat, which is minus x hat. So if I put that all together, I get that the magnetic field is mu naught over 2 pi, I over rho, minus sine phi, x hat, plus cosine phi, y hat. So this is actually a pretty easy expression. When I'm done, I get the constant, I get the current divided by the distance away, and then times this combination of trigonometric factors. Now, if you're like me, this doesn't give you a lot of intuition for what's going on, because in Cartesian coordinates, it's kind of funny to think about minus sine phi and cosine phi as being a vector. Well, it makes a little bit more sense if I switch to the frame where I'm looking down the axis of the wire. Here, my point of interest, and it doesn't matter where I am along the z-axis due to symmetry, so I'm just going to choose some constant z surface, okay? But I look at x prime and y prime, and I can look at that in terms of the two variables that I'm looking at, rho and phi. So if I am looking at some point in the positive quadrant, right, so now x prime and y prime are both positive, then my magnetic field is pointing in the negative x hat direction and the positive y hat direction, where the magnitude of those two things are given by the trigonometric identities as minus sine phi and cosine phi. Therefore, the magnetic field B is actually pointing tangent or perpendicularly to the r vector, and it's pointing left and upward, right? It's pointing in the positive y hat direction and in the negative x hat direction. Now, if I kept repeating this, I would find that this magnetic field is sort of always pointing perpendicularly to the r vector in the x prime y prime plane, and that the trigonometric identities are causing it such that it's sort of always pointing to the left if I'm pointing in the r vector direction, right? And so the magnetic field in this case is always pointing around the circle. It's pointing in the phi hat direction, right? It's always going to be pointing in the phi hat direction, and it only depends on phi, right? This is actually a unit vector in the phi hat direction. And so if I'm looking down any wire, the magnetic field lines are going to wrap around that wire in the positive phi hat direction. That is to say, if your thumb on your right hand is that wire, it's pointing in the direction of all of the fingers on your right hand. And so this is another right-hand rule, right? So the magnitude of the magnetic field depends on how far away from the wire you are and how much current there is through the wire. But the direction is always going to be tangent to how far away you are, that is perpendicular to the r vector, and it's always going to be pointing according to the definition of the right-hand rule. So if the current's coming towards you, it's going to be going counterclockwise. If the current's moving away from you, it's going to be going clockwise. But the magnitude is always going to fall off as 1 over the distance. Okay, so here are your take-home messages. Generating magnetic fields is mathematically challenging, right? This is the Biot-Savart law is hard. It's got a cross product and it's got an integral in it. But currents create magnetic fields according to a right-hand rule, and that's sort of an easier thing to conceptualize. And then the magnitude of those magnetic fields are falling off as 1 over the distance away from the current. I called it rho in the previous place because that was the variable that I defined in polar coordinates. But 1 over the distance away is how I talk about the strength of a magnetic field due to a current carrying wire.